Hello boys and girls, welcome again to some helps with some problems. Today we're going to look at a case where you actually might have done this. It's a projectile motion problem, but in this case what we're going to do is kick a football. And this football we're going to kick at with an initial velocity of 18 meters per second at an angle of 40 degrees from the horizontal. What we want you to do in this problem is calculate the horizontal and vertical velocities of the football. Not immediately, but 1.4 seconds later. So this sounds like a complicated problem, but it's not really. By the way, when we've done that, we also want to determine which direction it is moving. So to start with, we need to know that x and y are independent. And we need to solve for those two separate velocities, both the velocity in the x direction and the velocity in the y direction. This is my Vy initial, this is my Vx initial. This is not really a hard problem because in truth, this is just a triangle.
Now to speed things up a little bit, we've done some of the math already. Notice that here we have drawn out that resultant triangle. We have the 18 meters per second at 40 degrees, and we've got then our horizontal velocity and our vertical velocity. Now from this point then, to divide that resultant velocity up into parts basically just requires us to do some trig. Notice that the horizontal velocity is the side that is adjacent to the 40 degrees. So we can see then that if we want to find the adjacent side, we would be using the cosine. So if we do a little rearranging here, we would take our resultant of 18 meters per second and multiply that times the cosine of 40. That gives us 13.8 meters per second as our horizontal velocity. Okay, so right here then, when we say that that football is traveling at 18 meters per second at an angle of 40 degrees, that also means that it is traveling 13.8 meters per second to the right. Okay, we can do the same thing then in the vertical direction, only in this case the vertical side is the opposite side, and so for opposite sides we would use the sine. So in this case we would again take 18 as the resultant, multiply it times the sine of the angle, and this time we get 11.6. That then is the vertical velocity. So again, as our football travels with a resultant of 18 meters per second at an angle of 40, that means it's traveling upwards at 11.6 meters per second.
We've already solved for the horizontal velocity because we know that nothing is affecting the horizontal. So this is our final answer in the horizontal direction. There's nothing more we need to do about that. It's not going to change. The velocity is constant. But it is going to change for the vertical direction. And the reason for that is gravity is acting on this. So we need to go back to our kinematic equations where we know, and what we're solving for is our final velocity in the y direction. We know our initial velocity in the y direction, and we know what is acting on it, which causes the acceleration, and we know the time, which was given to us. So, our initial velocity in the y direction is 11.6 meters per second. The acceleration is simply gravity, but remember, gravity is negative because it's going down. Meters per second squared, and our time is 1.4 seconds. At this point, it's just a calculation, and when we're done with the calculation, we're going to get minus 2.12 meters per second. This is our final velocity in the y direction. So we've got both velocities, both components, at 1.4 seconds afterwards. We've only got one other question to determine, and that is whether the football is moving up or down. And strangely enough, our answer is right in the math. Because if you look at the final velocity in the y direction, it tells us whether it's going up or down. Simply because we have a negative velocity, it must be going down. If the velocity had been positive, we would know it was going up.
Hey everyone, here's your Sioux Falls physics teachers looking more at projectiles. Today we have a cannonball with a resultant velocity of 40 meters per second at an angle of 30 degrees from the horizontal. We need to determine the maximum height and the range of the cannonball.
One of the first things we need to do then is to break the velocity down into horizontal and vertical components. Since we know it's launched at a 30-degree angle and we know that that initial velocity is 40 meters per second, we need to find our v sub x and our v sub y. To find the v sub x, we're going to use the cosine. I will take cosine of 30 times 40 meters per second, and we'll get 34.6 meters per second. And then for the vertical velocity component, we'll take sine 30 times 40, and we'll get a value of 20 meters per second.
Okay, once we have those components, now we're ready to look for the time that this is in the air. Before we start that, we might want to kind of draw out a diagram of what this is going to look like. Here's our initial velocity. It's taking off over here. And then a couple things that we know about it. One is that when it reaches the top in the vertical direction at that point, its velocity is 0. That's where gravity has slowed the vertical velocity down to 0, and it's getting ready to come back down on the other side. The other thing that we know is that if we think about the horizontal velocity, that 34.6 meters per second is going to remain constant all the way through. So the 20 meters per second that we have here will be changing through the path, while the 34.6 will remain constant. The one determining factor then for time is the vertical velocity. So we will start with our velocity equation, and we're going to use that to find the time. Now we know that our initial velocity then in the vertical direction was 20 meters per second. And we also know, looking up here, that in the vertical direction at the top, that velocity is 0. So we can plug a 0 in here. Our gravity is our acceleration of -10, and we have an unknown time. Now if we solve for that, we get a time of 2 seconds. However, we want to be a little careful about that. Usually it's a good idea to write top there so that we remember that that's all the way to the top. Later, we'll also need the total time for it to go up to the top and come back down. There we would multiply by 2 because it is going to the top of the path here and coming back down, and so that gives us a total of 4 seconds for the total. We'll need both of those as we finish off the problem.
Okay, so we're now ready to find the height that this cannonball reached. We have our displacement, our distance formula here. So we're going to be solving for d. Okay, our initial distance is 0. We started on the ground, but we did have an initial velocity in the y direction of 20 meters per second. And we'll multiply that by our time. And again, we're just interested in the time it takes to get to the top of this. So times 2 plus... Okay, 1/2. Our acceleration is a -10 meters per second squared times that same time, 2 squared. And when you calculate that out, you get a distance of 20 meters.
Okay, now we're ready to find the range or the horizontal distance. Notice that if we go back to our distance equation, we don't have to worry about initial distance. We do have initial velocity in the horizontal direction, so we need to use that, but we don't have any acceleration. So in the x direction, we're left with just initial velocity times time. Be sure you use the horizontal part of the initial velocity, so that's that 34.6. And for the time, we're now talking about where it lands over here. So we do need to use the total of 4 seconds until it lands. And multiplying those out, we get a distance of 139 meters. This then would be the distance in the x direction, also the range of the projectile.
Well, hello everyone. Here's your Sioux Falls physics teachers wrapping up our study of projectiles with this particular example. Soccer ball kicked from the ground level with an initial velocity of 22 meters per second at an angle of 35 degrees. It strikes a tall building that is 15 meters away. Notice on our diagram that would be the horizontal distance. Determine the height, or the vertical distance, at which the soccer ball strikes the building. Well, as with any of these types of projectile problems, the first thing that we want to do is find our components of the velocity. So here we can see that we have an x component of the velocity and a y component of the velocity, and that together our resultant is 22. We will be needing both components, so we'll solve for both. The x component is adjacent to our angle of 35 degrees. So adjacent sides would be involving the cosine. So cosine of 35 degrees is equal to the adjacent side, or the Vx, divided by the hypotenuse, which is that resultant velocity of 22 meters per second. And that means that our x velocity is 18 meters per second. We can repeat the same calculations for the y component. The y component, however, is the opposite side. So the opposite side would be using the sine. So sine of 35 degrees is equal to the y component divided by the resultant, which is again 22 meters per second, and that gives us a y component of 12.6 meters per second. Now notice that in both cases these are initial values. In the horizontal direction, that's not going to be a big deal because horizontal velocity doesn't change, but in the vertical direction it is. When it first starts, first leaves the ground, that vertical velocity is 12.6, but of course that 12.6 will be changing.
Okay, now we need to solve for something. And remember that it is time that ties together the x and y direction, that ties together that velocity in the x direction, the velocity in the y direction. And it turns out this time is not hard to solve for in this problem. And the reason is we know two things. We know the velocity in the x, which is not going to change, and we know the displacement in the x, which is 15 meters. So as a result, we can go back to our simplest definition of velocity, which is the change in displacement over the change in time. We can even rearrange this equation to become the change in time equals the change in displacement over velocity. This is the velocity in the x direction only, and we know that velocity and that displacement. So it's 15 meters divided by 18 meters per second. When we solve that, we're going to end up with a change in time of 0.83 seconds. And this will be the time that the ball is in the air until it hits the building.
Now, once we have this time of 0.83 seconds, that will allow us to find the height or the vertical distance at which the soccer ball strikes the building. Now remember that really we don't know at this point whether or not that soccer ball is at its highest height. We don't even know, for instance, for sure, without doing some more calculating, whether it's on its way up or maybe on its way back down when it hits the building. All we know for sure is that if we look at the horizontal information from the time when it starts here, travels horizontally until the plane of the building, it takes 0.83 seconds. So basically what we need to do then is figure out in 0.83 seconds what height the ball will be at. For this, we'll go back to our longer position equation. And again, remember that really this position equation has three terms. We have initial position, which is not a factor here. We're starting at ground level. We have initial velocity times time, and we do have an initial velocity, so we'll leave that in. And we have the last term of 1/2 acceleration times time squared. So basically we want to fill these things in, being sure that we put in vertical components, and that will then give us our final vertical position. Our initial vertical velocity can be found here. We found that as our component of the triangle, and that was 12.6. Our time, again, is 0.83 seconds. Adding the second term, we have 1/2. Acceleration, we need to be very careful to make that a negative 9.8. And 0.83 seconds, again, squared. And working out the algebra on this, we get a final vertical position of 7.11 meters as the height at which the ball strikes the building.
Well, hey everyone, this is Mrs. Newitt.
And this is Mr. Newitt.
And here we're looking at another problem with your Sioux Falls physics teachers, this time on projectiles.
So we've got a desperate punter that is kicking a football. That football is going to go 50 meters, and that's about 55 yards. Pretty good punt. Downfield. It has a hang time of 3 seconds. And what we're looking at here is we want to see, can we figure out, based on that data, what the initial velocity of the punt was?
And notice, if you've watched any of our earlier broadcasts, we've kind of already walked through how you could take an initial velocity and figure out how high and how far it's going to go. This problem's simply doing the reverse. And we should probably make note, you can easily see how far it goes, a lot of network, so it'll give you the hang time. So this is one of those little calculations that'd be pretty easy to do on your own. So what are the things we need to remember first? Well, similar to our other broadcasts on projectiles, the first thing we need to do is look at our equations. And remember that there are two basic equations. One is the equation for velocity, and that is that the final velocity is equal to initial velocity plus acceleration times time. The second equation we'll be using is the one for position. Okay, the distance of an object is equal to its initial distance plus initial velocity times time plus 1/2 a t squared. Now remember that both of these equations then, when we apply them to projectiles, the important part is simply to determine which pieces of those equations we're going to need.
All right, now let's remember a few things about the motion of this football. Remember, like we've been discussing, anytime we have projectile motion like this, we want to break this down into the horizontal and the vertical pieces of the motion. Remember, those are completely independent or separate from each other. So horizontally, the football is going to have a constant velocity. Whatever initial velocity it's given in the horizontal direction is going to stay in the horizontal direction the entire flight of the football. We are assuming no air resistance here. Vertically, the football's initial velocity is going to be affected, obviously, by gravity. So as the football goes up to its highest point, at that highest point it will have 0 vertical velocity, and then it will begin to make its descent back down to the ground. Remember, in these situations, that the vertical velocity that the football hits the ground with would be the same vertical velocity it is launched at, or in this case, punted.
All right, so let's take a look then at some numbers. And we've got a little diagram of our football's path drawn here. Note that right now we don't necessarily know whether or not it's to scale or not. But we do know then that it has a resultant velocity that is going to be at an angle. And that resultant then can be split into those 2 parts, one in the x direction and one in the y direction. The other piece that we may want to add to our diagram is some information about the time. Notice that the hang time is given as 3 seconds. And that means then that it is 3 seconds from the time that it is initially kicked all the way until it reaches its end point over here. And so we may want to even write this down. And again, usually I think it's a good idea to maybe put a little subscript there that reminds you that hang time is the total time of 3 seconds. The other place that is an important point to us, and we'll be using this here in a minute in our calculations, is that top point. And again, as we mentioned, that's because that's where in the vertical direction it comes to a stop. So we know some information up there. We know that the vertical velocity at the top of its path is 0. We also know that that's going to be halfway of its total flight. So the time, or half of its total time at that point, would simply be 3 seconds divided in half, or 1.5 seconds. That's going to then allow us to begin our calculations for velocity.
All right, well, let's go ahead and do the vertical velocity first. So as we're going to look at this, we are going to use that midpoint that we were just talking about, where we know that the vertical velocity is going to equal 0. And we'll go ahead and kind of let that be our v sub f, or our v sub final in the y direction. So we're going to say that that is 0 meters per second. That will be the top of the flight here. All right. Now, the reason we're going to be really focusing on the velocity is we actually know nothing about how high this football went. So our second equation here is really not much use to us for the vertical velocity. All right. Now, what are we trying to find? We're trying to find the initial velocity in the y direction, and that's our unknown. Okay, we don't know what that is. Do we know anything about the acceleration in the y direction? Well, we certainly do. Acceleration in the y direction is gravity, which is working downward, so we'll say that is negative 9.8 meters per second squared. And we know the time that is involved here, and again, we have to be careful. We're interested in this top point here. That's our ending spot for what we're looking at. So the time is not 3 seconds, but rather 1.5 seconds. All right, now we have enough information here to plug into that first equation to solve for our initial velocity. So 0 meters per second is our final velocity in the y direction, is equal to v initial in the y direction, that's our unknown, plus negative 9.8 meters per second squared for the acceleration, times that time of 1.5 seconds. All right, so just a simple multiplication here and a little solving, and we will get an initial velocity in the y direction that's equal to 14.7 meters per second.
So now we've got that vertical component of velocity. Next we want to take a look at the horizontal. And notice that in this case, we actually do have enough information to use our distance equation, because in the horizontal direction, we know the distance that it travels. Now, one thing we talked about again in earlier broadcasts is that we've got a big, long distance equation here. We don't necessarily need to use all of those terms.
So what do we know about the horizontal direction? Well, first of all, we are looking for that initial velocity in the horizontal direction. That is our unknown. We also know that without air resistance, there would be no acceleration. Now remember that little simulation we saw of the football at the beginning? It does not speed up or slow down in the horizontal direction because gravity is not acting on it in the horizontal direction. So that means then that if we look at our distance equation, this last term that includes acceleration is not needed. We have no acceleration if we're working in the horizontal direction. We also can eliminate the initial distance because we're assuming it starts at an initial distance of 0. And finally, we have its final distance or its final position, which is that 50 meters that it traveled downfield. What we are left with then in the horizontal direction is this. Distance is equal to horizontal velocity times time. And again, in this case, our 50 meters takes us all the way to the end. So the time that we want to be including here is the full 3 seconds. So we have 50 meters as our distance, unknown velocity, multiplied times 3 seconds, and then we can finish up the algebra, and we get an initial velocity of 16.6 repeating meters per second. So if we take a look, we now have values to plug in to our diagram that's listed above. In the y direction, we had an initial velocity of 14.7, and in the x direction, an initial velocity of 16.6 repeating. Notice then that actually our diagram was reasonably close to scale because those two components are reasonably close to the same amount, and that tells us we do have close to a 45-degree angle.
All right, now that we know the initial y direction velocity and the initial x direction velocity, we're ready to actually come up with our answer. Remember, our answer says calculate the initial velocity of the punt. So what we need is the resultant amount, which is going to be this velocity. So we have to use a little Pythagorean theorem here. We have a right triangle set up, and we know the two legs of the triangle. So essentially, v sub x squared plus v sub y squared will equal our resultant velocity squared. So if I put 16.6 repeating and square that plus 14.7, square that, that will give me my resultant velocity squared. And just doing a little bit of the math there with that, you'll get a resultant velocity amount of 22.2 meters per second.
So that means then that our football left that punter's leg with a velocity of 22.2 meters per second, which translates into 14.7 meters per second up and 16.6 repeating meters per second to the right. However, we are actually not done yet. Notice that the question simply says, what is the initial velocity? And velocity is a vector. So if we have a vector quantity, our answer is not complete without knowing this angle. Okay, so we can know that it's going at 22.2 meters per second, but what angle was that exactly? Well, the easiest way to do this is to go back to a little bit of trig. We have 14.7 and 16.6 repeating as our two sides. And when you are dealing with the two sides of a right triangle, they are related by the tangent. Okay, tangent is opposite over adjacent. The opposite side in this case is the Vy. The adjacent side is the Vx. So we would then have tangent of our angle is equal to 14.7 meters per second divided by 16.6 meters per second, and that will give us then an angle of 41.4
degrees. So again, just under 45, which actually means that our punter was wise in the ways of physics because he ended up pretty close to the maximum range, which would have been at a 45-degree angle. So 22.2 meters per second was the velocity of his punt at an angle of 41 degrees.